Okay, so today we're going to do formal charge and a few other things as well. All right, formal charge is, here's your definition of it right here. It's your valence electrons minus the number of electrons around an atom in a structure. I'll show you how to do that. And the only reason, well, not the only, but the reason why we care about formal charge is because sometimes there are two possible Lewis structures, and we use formal charge to identify which structure is more correct. We pick the structure that has the least non-zero formal charges, the most zero formal charges. We want formal charge to be zero. So we're not going to do that whole picking a Lewis structure that's more correct right now. First, we're just going to identify how to figure out Lewis structures. How to figure out formal charge. Okay, so CO3 minus. We hadn't done ions before. Here's your Lewis structure for CO3 minus. You add 2 electrons for that -2 charge there. So there's your structure. And first we're going to look at the formal charge on the left O. And here we go. We have 1, 2, 3, 4, 5, 6 electrons that oxygen owns by itself, and then these oxygen and carbon are sharing these two. We only count this as 1 when we are doing formal charge. So this counts as 7 total electrons around the oxygen, and the definition was valence electrons, which is 6 for oxygen, and then we subtract the number of electrons around the atom, which was 7. So the formal charge on this oxygen would be -1. 6 minus 7 is -1. You can pause and do this yourself for the charge for the right O, or you can just copy this down. On the right O, we had 4 electrons that belong only to oxygen, and then we have 2 bonds, so 1 electron belongs to oxygen for this formal charge analysis. And another electron belongs to oxygen, so oxygen has 6 electrons around it. 6 minus 6 is 0. This oxygen would have a formal charge of 0. And the bottom O and the carbon, you should pause this, do these yourself. I'm going to show you the answers in just a moment. You should pause. All right, so the oxygen has 7 electrons around it. The bonds count as only 1 for formal charge. And 6 valence electrons minus 7 is -1 for this oxygen right here. And then for the carbon, carbon has, in this structure, has 1, 2, 3, 4 electrons around it. And carbon has 4 valence electrons, so 4 minus 4. Carbon would have a formal charge of 0 in this structure. Now your turn, you're going to do these on your own. Pause this, and I'm about to show you the answers. Okay, so left side, the top and bottom oxygens would be the same. We've got 6 plus 1, 7 total electrons around them. So this is this one right here. 7 electrons around it. 6 minus 7 is -1. So these 2 oxygens have a formal charge of -1. These 2 oxygens have 1, 2, 3, 4, 5, 6 electrons around them. 6 minus 6 is 0, so the oxygens would have a formal charge of 0. And the sulfur in the middle here, sulfur has 1, 2, 3, 4, 5, 6 electrons around it, and sulfur has 6 valence electrons, so that sulfur would have a formal charge of 0. Okay, some girls are in the room, so if you hear background noise, it's just students zippering up bags and things. It's okay. All right, now notice all these oxygens are the same. They all have 1, 2, 3, 4, 5, 6, 7 electrons around them. And oxygen should have 6 electrons around it in terms of valence electrons. So the formal charge on all the O's is -1. 6 minus 7 is -1. And sulfur has 1, 2, 3, 4 electrons around it. Sulfur has 6 valence electrons, and 6 minus 4 is +2. So between these two structures, the one on the left, this one, right? I can't highlight it the way this thing works. This SO42 minus would be the more correct version because it has fewer atoms with a non-zero formal charge. Okay, and notice they had brackets around them because they are polyatomic ions. Anytime you have an ion, you put the brackets around and put the charge outside the brackets. Okay, resonance. This happens when you have more than one possible Lewis structure for a molecule. An example is SO3. We have 1, 2, 3 different structures that are all acceptable for SO3. So these would have what is called resonance. And we're going to talk about bond order, new concept. And bond order is the number of atoms, number of bonds between two atoms. A single bond would be bond order 1, double bond would be bond order 2, a triple bond would be bond order 3. Okay, now with resonance it gets a little tricky because this second bond right here spends a third of its time on the left, a third of its time on the right, and a third of its time on the bottom. Notice there were 3 different structures and the bond is in 3 different places. So we would say that that bond spends 1/3 of its time in each place, on the left, on the right, and on the bottom. And since it's divided among 3 places, it's only considered 1/3 of a bond in each place. So the overall bond order for this molecule would be 1.33. We would say between each S and O, there is 1 1/3 bond, because one of the bonds just stays where it is. It just stays put. You'll see in each of these, there's the single bond is always there. That second bond is the one that moves. So now you're going to try on your own. You're going to do SO2. So you should pause and get your structures for SO2. Hopefully you paused. All right. So here are the 2 structures. There are only 2 of them. And you have to put those arrows showing that the Lewis structure goes back and forth between the different structures. And notice, you'll notice that there are 2 structures, and that second bond will spend half its time on the left, half its time on the right. So notice I'm saying there's 2 structures, so it spends a half a time in the left, half on the right. So the bond order would be, what would it be? 1.5. Hopefully you got that right. Okay, now try NO3 You should pause and draw the structures. Don't forget your brackets. You add 1 electron because of the 1 minus, so you add up all your valence electrons plus 1 more. You should pause. Here are your 3 Lewis structures. And now for the bond order, we've got a single bond everywhere plus 1 double bond, but that second bond spends its place in time in 1, 2, 3 places. So it spends a third of its time in each place. So the bond order would be 1.33. Okay, bond energy. This is the energy needed to break a bond. When a bond forms, energy is given off. That's exothermic. And when you break a bond, you have to put energy in, which is endothermic. And these are all the bond orders. Sorry, the bond energies for different types of bonds. And when we can calculate heat of reaction with these bond energies, but it reverses. Instead of doing with heats of formation, we have products minus reactants. Here we do reactants minus products because breaking bonds, the reactants, is endothermic, positive. Forming bonds is exothermic, negative. Totally different from using heats of formation. Okay, so to find heat of reaction for a reaction, we have to first draw our Lewis structures. You could do this yourself. I'm about to show you the Lewis structures. Oops. Okay, so we have an NN triple bond, 3 HH bonds, and 6 NH bonds. That's a little tricky. You have 3 NH bonds times 2. So we have 6 total NH bonds. And then we just use the data up here. We look up an NN triple bond, right there, 941, plus the other reactants, HH, 3 times 432, minus, because we're going to minus our products, minus 6 times, where's the NH? 391. And hopefully this answer is correct. You can check the math on that. Okay, last problem for this video. Do your Lewis structures. I'm going to pause for a moment, and you should do the Lewis structures. You should pause your video. Here are your Lewis structures. So I've got 4 CHs, 2 OO double bonds, 2 CO double bonds, and 1, 2 times 2 OH bonds. And so 4 total OH bonds. We look up the values for the different things up in the chart right here. And notice that the CO double bond is 799 for CO2. There's little asterisks there. So be careful when you're subtracting your products. Some people forget to subtract this second part. And there's your answer. And that's it for today.